In this video, we're going to talk about quadratic models. So there's lots of things that we can model with the quadratic function. So we're first going to start with maximizing revenue. So modeling revenue with a quadratic function. So let's first define revenue. So revenue is the amount of money received from the sale of an item, okay, and is equal to, so we normally call it R, that's a weird R, we normally call it R, okay, and we normally say it's equal to P times X, okay, where P is the price per item, okay, and X is the number of items you sell. Okay, so the revenue is the amount that you make on all your items. So you want to take the number that you sell multiplied by the price that you sell them at, and that's going to equal the amount of money that you received. Okay, so let's consider this example. So suppose we charge a price P, okay, and then we know that the number of goods sold is going to be X. Okay, and we have this equation, X is equal to 150 minus 4P. So the number of items sold depends on the price that we charge. And now we want a function for the revenue, R, in terms of the price, P. And then we're going to find the maximum revenue possible. So first of all, we know that the revenue is P, the price, times the number sold. Okay, and I know that the number sold in terms of P, so that's going to be, so let me just, okay, so X I can replace with 150 minus 4P. So this is going to be P times 150 minus 4P. And then if I expand the P in, it's 150P minus 4P squared. Okay, so that means that the equation for the revenue in terms of the price is minus 4P squared plus 150P. Okay, so that's what we're working with. Okay, and you might notice that this is a quadratic equation. Okay, so this, because of the P is squared, the highest power. Okay, so this is a quadratic function in terms of P. Okay, and the A value is equal to minus 4, which is less than 0. Okay, so that means that it has a maximum value, right? Because it opens down. So the vertex is going to be where the maximum occurs. Maybe I'll just write that. Okay, so the maximum revenue will occur at the vertex. Okay, so to find the vertex, remember that the vertex is at, so it's going to be P instead of X, but it's negative B over 2A. Okay, so here A is equal to negative 4, B is equal to 150, and C is 0 because there's no constant term. So this is going to be negative 150 divided by 2 times negative 4. Okay, so that's going to be negative 150 over negative 8, which simplifies to 18.75. Okay, now this is the price, the P. Okay, so this should be in dollars. Okay, so the maximum revenue occurs when the price is that, but we actually want to find the maximum revenue. Okay, so we just found the price at which it occurs. Okay, but we want to find the maximum revenue. So, max revenue occurs when we charge the price $18.75, okay, which implies that the max revenue is, so I just plug in 1875 into my formula. So it's going to be -4 times 1875 squared plus 150 times 1875. So if you simplify that, put it all together, it's $1,406.25. Okay, and that's because the vertex of our parabola is at 1875, and this is its R value, or its Y value. Okay, so that's our max revenue. And then it also wants to know how many goods will be sold at this. How many goods did we sell? Okay, so to achieve this revenue, we sold, so now we want to plug into X. Okay, so remember X was 150 minus 4P. So it's going to be 150 minus 4 times 1875. And if you compute that, you get 75. So we sold 75 items. So that answered all the parts there. Okay, so for solving many types of max-min problems, so here we didn't, but we could have drawn the picture. But sometimes it helps to draw a picture to figure out where your variables are. So it helps to identify which are variables, and to establish any known relationships between these variables. And then you're going to have to rewrite the optimization variable, so the thing that you want to find the max-min of, in terms of only one other variable. And then you can find the vertex, so you can use the formula like we just did, or you can put it into the standard form so that you can see the vertex, whatever you prefer. And then obviously read the question again and make sure that you solved the problem. Okay, so let's try one where a picture might be useful. So a farmer builds a rectangular fenced pen along a river. Okay, they have 300 feet of fencing available, and they want to know what is the maximum area they can enclose. And obviously they're not going to need a fence on the riverside. Okay, so let's see our picture. Okay, so on this side is the river. Okay, and then we have our rectangular pen. Okay, and we don't know how big it is. So we can define our variables, right? So let's say this is X and this is Y. I should have gone the other way. Let's switch it. So let's say this is Y and this is X. So the X is the horizontal, Y is the vertical. Okay, then we know right away, because it's a rectangle, we know how to find the area of the pen. It's going to be X times Y. Okay, but we only want the area in one variable. So what we're going to do is we're going to need to replace one of those variables. So we need to use the fact that they only have 300 feet of fencing. So they want to make this pen as big as possible. So they're probably going to use all 300 feet of fence. So that means that this length here is equal to 300. So that's going to be Y plus X plus another Y. Okay, but we also know that the 300 should be equal to 2Y plus X. Okay, so we can use this to get rid of one of the variables. Okay, so I'm going to get rid of X here because it's a bit easier to solve for. So rearranging gives x is equal to 300 minus 2y. Okay, so then the area, which was x times y, is now 300 minus 2y times y, or 300y minus 2y squared. Okay, so now I've made it a bit weird because that's okay. So this is a quadratic function. Okay, so that's just right here. So this is quadratic. Okay, and the a is the thing with the y squared, so that's minus 2. The b is 300, and the c again is 0, because there's no constant term. So that means that the vertex, and it opens down, so we do have a maximum. Okay, so that's good. We're looking for the maximum. Okay, so the max area occurs when y is negative b over 2a. So negative 300 over 2 times negative 2. So that's negative 300 over negative 4, which is 75. Okay, so when the y length is 75, we get the maximum area. And the maximum area, I can just plug 75 into my area equation. So that's going to be 300 times 75 minus 2 times 75 squared. And I'm going to get 11,250 feet squared, because it was in feet, the units. Okay, so that's the maximum area. It occurs when the y side length is 75. Now, if it wanted the dimensions of the pen, which it doesn't actually say, it just wants the maximum area. So this would actually be our answer, because that's what it was looking for. But if it wanted the dimensions, we could find the x dimension. So x is 300 minus 2 times 75. So that's going to be 150. So it could have asked for the dimensions. And then the dimensions of the pen would be 75 feet by 150 feet. Okay, it didn't need that, but it could have. So let's look at this last one. I'm going to leave it for you to do, but I think I'm going to help draw the picture a bit so that you can get an idea of what to do. So the Golden Gate Bridge has 2 end towers that are 4,200 feet apart. Okay, so I'm going to start by drawing those. Okay, oops, that's not very good. Okay, so those are our towers. They should be the same height. And we know that they're 4,200 feet apart. Okay, so I know this distance is 4,200. Those are our 2 towers. Also, each tower is 746 feet tall. So we also know this height is 746. Okay, for both of them. Now, a cable is hung from the top of each tower and touches the bridge in the middle. Okay, and it's parabolic in shape. So then we have from the top, okay, of each, which are the same height, we have this parabola shape that touches the bottom and goes up. Okay, now because the parabola is symmetric about the middle, that means that the 2 towers should be equally distant from this middle point. Okay, so that means that this distance, actually I want that to be a bit higher. This should be half the distance, so 2,100. Okay, on both sides. So half. Okay, so that's the idea. So now, suppose another tower is going to be erected 1,000 feet from the center of the bridge. Okay, and we want to know, so this is the new tower. Okay, so there's our new tower, and we know that this distance here is 1,000. Okay, and there's, I guess, one over here as well. Oops. Okay, so this distance is also 1,000. So we want to know how high it needs to be. Okay, so we want to know the height. Now, to help us, we want to sort of plot this on the plane. So you can do this in lots of ways, but I think it's going to be easiest if we plot this vertex at 0, 0. Okay, because then the coordinates of this point are going to be 2100 and 746, the height. And the coordinates of this point now are negative 2100 and 746. Okay, so that might help us, because now this coordinate that we actually want to find, okay, has x value 1,000, and I only wrote 100 down here. Okay, x value 1,000, and then the y value we don't know. Okay, and that's what we want to find. Okay, so I'm going to leave that for you, but that's sort of the picture, and I think the easiest thing to do is to plot the vertex in the center. It's going to make your formula a bit easier to work with. Okay, so take a shot at that. Try and find the height of this tower here. So that are some models that involve quadratic functions.